So in the previous class, we learned about the multiplexer, right? So what is a multiplexer? So multiplexer means that based on the selection signal, as multiplexer has multiple, so that's why it's called multiplexer, right? So multiplex has multiple inputs and then one output, and then input. So based on the selection signal, the select input, and then this selection signal is also called the control input. So based on the select control signal, the output is connected to the one of multiple input ports. Okay, that is the definition of a MUX. Okay, and then we can generate the truth table for COSE221 multiplexer. And then based on the truth table, then we can generate the Boolean equation, the sum of a product form. Okay, and then we can generate the Boolean equation. Also, we can implement multiplexer using twice state gate. If you understand the definition of a multiplexer, it means that its output is connected to one of multiple inputs, and then actually you can control the connection and disconnection of this tri-state gate using the selection signal. So it means that we can implement the multiplexer using this tri-state gate. Okay, and then we can also consider the 4-to-1 MUX. Then we can for this 4-to-1 MUX, we can implement the 4-to-1 MUX hierarchically, or also we can consider the two-level logic or tri-state gates. And then in the previous class, we also learned about the additional SystemVerilog syntax. And then actually, especially, and then we learned about the always statement. And then, so we are learning about the new statement in SystemVerilog, so which means that you need to understand, you need to memorize the definition of this statement. And what is the definition of always statement? So as I mentioned, the always statement has the sensitivity list. So which means that if condition defined in sensitivity list are met, which means that the conditions are true, then statements inside of this always statement are executed. That is the definition of always statement. And then actually in SystemVerilog, we frequently use always statement. Okay, because inside of the always statement, then we can define multiple statements. And then so another statement we learned is assign, right? But in assign, we can just define the one output, right? So when we define assign statement, we just define the value of output, the one output. But in the always statement, we can define multiple statements, and statement 1, statement 2, blah blah blah. Okay. So actually, we frequently use always statement in SystemVerilog. And then in SystemVerilog, there are 3 kinds of always statements. That those are always on the com, so which is that it's used for implementing combinational logic. And then we do not learn about the sequential logic, but for implementing sequential logic, we use always and the FF means the flip-flop. And then we can also use the always on the latch for implementing latch. Okay. So this is the example of always statement, right? It's device. So also, so So in this always statement, I implement the bitwise operators in SystemVerilog, and then the multiple outputs. As you can see, the inside of the always statement, you can define multiple statements. We can define multiple outputs here. Okay. And then also I mentioned that in SystemVerilog, we don't need to define sensitivity list for combinational logic, right? Actually, this is the definition. Definition of the always statement is that so always also includes the sensitivity list, and then which means that if the conditions in sensitivity list are met, then always statement is executed. But as you can see, in the always on the com statement, we do not observe the sensitivity list. And then I mentioned that actually the SystemVerilog generates the sensitivity list for this code. So actually, in order to generate the multiple outputs from Y1, Y7, then we require input signals A and B. So which means that output signals are defined by two input signals, A and B. So actually, when we define always conventional, so the classical always statement, then we need to define sensitivity list using A and B. So which means that A or B should be included in this always statement. But it can generate. So actually, we can omit some sensitivity, some signals in the sensitivity list by mistake, and then it can be a critical bug. So what is the critical bug? So we use our design module for simulation and synthesis, but the simulation and synthesis can be different. So which means that our intention is to generate this module. But if we omit some signals in the sensitivity list, then simulation can be different from the result of synthesis, right? Because the always statement works when the sensitivity list, the conditions in sensitivity list are met, right? So that is the simulation. But when these modules are synthesized, then the cat will just analyze the operators of SystemVerilog and then cat to generate some basic things like the AND or exclusive for this module. Okay, so which means that if we define the wrong conditions in the sensitivity list, then the simulation, the result of a simulation can be different from the result of synthesis, and that can be a critical bug. Okay, but in the SystemVerilog, we don't need to define sensitivity list for combinational logic, so we can just use always on the com. Okay, it's very convenient, right? So actually, this is in Verilog, we need to define sensitivity list for always statement. Or we can also define like this, like head and austerity. Okay. Okay, so that's what we learned in the previous class, and then let's learn about the more statement in SystemVerilog. Then another statement is the if else. So it's very so you can frequently observe if else statement in normal programming languages such as C, also in Python. So you can also use the if else statement in SystemVerilog. And then in order to use the if else statement, we also need to use the always statement. The if else statement should be defined inside of the always statement. Okay, So in order to use the if else statement, then the if else statement is defined inside of the already statement. That's very important. So we cannot use a sign for this if else statement. So if you want use a sign statement for if else, then we can use the ternary operator like condition and A works with. Okay, we can use ternary operator for implementing if else statement using a sign statement, but in the already statement we cannot use if else statement. Okay. Okay. Compared to the ternary operator, this statement is it's easier, right? Actually, we can understand the definition of this if else statement more easily. Okay, so we can use the if else statement like this. So let's see the structure of if else statement. Okay, so what is the structure? So in order to use the if else statement, then we need to also use condition. So if else statement also requires condition. And then what is the definition? It's the same to the normal programming language syntaxes, like if else of C, which means that if condition is true, so if the condition follows if syntax. So if this condition is true, then statement A is executed. Else, if the condition is false, then statement B is executed. Also, if we can also define multiple statements inside of the if else, then we need to use the begin and. If we want to define multiple statements inside of the if else. So it's very simple. I can define based on the condition. Statement A can be executed or statement B can be executed. Okay. Then also, what is the true? If this condition is not zero, which means that actually, so we are handling digital signals inside of the SystemVerilog. So which means that if this condition is 1, which means that it's true. Okay. So sometimes you can observe the EN is the signal, and then I just use EN like this, which means that if EN is equal to 1, which means true, and this condition becomes true. The statement A is executed. And if the EN is 0, okay, and statement B is executed. The 0 means false, 1 means true. The if else statement. Okay. And then actually, when we implement the combinational logic using if else statement, then we need to define all possible conditions inside of this if else statement. So what does that mean? Okay, so if we read this sentence, the if else conditions should be defined for all possible if conditions. And then so this is condition of if else statement. So when we use if else statement for implementing combinational logic, then our if else statement need to define all possible values of this condition. Okay, if not, then latch is generated. So we do not know about the latch yet. But if the latch is, so usually we do not use latch in the physical design. So we use latches for the special design, like some QM. But usually we usually we do not implement latches. That is the design. So which means that if latch is generated, which means it's a critical bug. Okay. So, but it's very important. If we do not define all possible conditions, all possible values inside of this if condition, then that will be generated. So, for example, box. So this is the selection signal, and then this is the A, and this is the B, and then this is the out. And then we can use S for this condition, right? So which means that if S is 0, then A is selected, and if S is 1, then B is selected, right? So, and then this S is the signal, so we can define two possible signals for S. So it's like this. If S, then O equal B, else O equal A. That is the behavioral model of this multiplexer, right? The same, right? If S is 1, then B is selected for output O. Then if S is it's not, okay, otherwise S, then O is connected to input A. But so which means that in this condition of all possible values of S is defined in this if S statement, right? But if we just omit the S statement here, so what's the problem? So in this if statement, we just define the result of S for S is equal to 1, right? We do not define the result of S is 0, right? You understand? We just define the S for S is equal to 1. So S is equal to 0 is not defined because we do not use else. So in this case, if S is equal 1, then O is connected to B. But for if S is 0, it's not defined. Then try to generate latch that is multiplexing. We have to just generate the latch because all possible conditions are not defined in this statement. Then it's a bug. Okay, it's just a bug. Because this is our intention. So we want to implement multiplexer using if as statement, but let's generate. It's a bug. It's very important actually, the SystemVerilog design. So you need to remember that when you use if as statement, that is the condition statement, and then if we want generate combinational logic using if as statement, then you need to define the result of this statement. And so which means that you need to define all possible conditions. Okay, it's very important. So this is the example of a bug. So the A is the input signal. So and then A is the 2-bit signal, right? The A is the 2-bit signal. And then when I define the if statement here, then we just define A is equal to 0, 0, and then also if A is equal to 0, 1, 1, 0. So what's the problem? Because A is a 2-bit signal, and we already know that 2-bit signal can have 4 possible values, right? So 0, 0, 0, 1, 1, 0, 1, 1. But when I use the if statement, I just define three conditions, right? One is missing here out of four possible conditions. So when this logic is generated by insurance data synthesized, then can to generate the latch and multiplexer. Okay, so it's above. Okay, so you need to read. So I also explained that we use SystemVerilog for designing these systems. Okay, so which means that so our module will be synthesized into, and it's a hardware. So which means that our hardware, so based on the SystemVerilog code, correct hardware should be synthesized. That's very important. But this code will generate the incorrect hardware, right? And then, as I mentioned, inside of the if else statement, we can also define multiple statements. Then we need to use the begin and end, right? So like so there's the begin and the inside of this if condition. So the true condition, there are multiple statements here. And then also this is the false condition, it's else. So multiple statements are defined inside of this false condition, right? So we need to use the begin and end for defining multiple statements. Okay, so this is the if else statement. Then I think you can easily understand the syntax of if else statement. Then another conditional statement is the case statement. So actually, this case statement is very similar to the switch of the language. Okay. So actually, the case statement is very similar to the if else statement. So which means that based on the condition, then based on the value of a condition signal, value of a signal, then we can define the statement. Okay, that is the case statement. It's very similar to the switch in C. Okay, switch is also definition of the switch is the same. So based on the value of this condition of the switch, then we can define multiple results, right? Okay, so let's see the example. So case statement. The case statement also needs to be defined inside of the array statement. Okay, so you not use the if else or you not use case statement. Then this statement needs to be defined inside of the arrays. So we cannot use assign, okay, for this case. The case statement, we also need to use the array statement. So combination also, which means that we can use the case statement for implementing combination of the flow as well. I'll use the array of com statement. So which means that I use this array statement for implementing combinational logic. Okay, and then the case starts with the case, then case ends with the end case. Okay, so and then after this case, then we can also define the variable. Okay. And then we can also define multiple statement based on the result of the variable. So we can say the condition 0, the statement A is executed, and then the condition is 1, and statement B is executed. And then default means the otherwise. So which means that for other conditions, otherwise, then statement B is executed. Okay, and then it's also important. It's the same for the case statement. So which means that when we use the case statement, so this is the condition. So this means becomes the condition of the case statement. So which means that we need to define all possible output or all possible control signal, like all possible conditions. So for example, what is the example? So this example shows the 7-segment of the coder. Okay. So it means that the input signal is the norm signal. So as you can see, norm is the 4-bit signal. So which means that it's a 4-bit signal. Then you can define 16 different values, right? It's a 4-bit signal, right? Okay. And then the norm is the condition of a case statement. So which means that if we use the case statement and then if norm is used as the condition of a case statement, then we can define all 16 conditions. So we can define all 16 cases. Okay, so what does that mean? And then this is the output, the set. So this case statement shows that if the norm is equal to 0, then that becomes the second bit signal, okay, 1 1 1 and 1 1 1 0. Okay, if the norm is equal to 1, and this is the output, and then blah 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 blah, and then it's very important before. So actually, and then this 7-segment means that in the calculator, so you can find the easy. Okay. And so we can display number, digit of numbers using the 7 bar, right? This is the 7-segment. It's called the 7-segment. So actually, sorry, if we use the calculator display, then the number or digit, it looks like this, right? Then actually it has got 7 bars. Okay, so so which means that 7-segment means that number 0 becomes the okay, so which means that this number is encoded to turn on the each bar of 7-segment. Okay, the 7-segment includes the 7 bars. So which means that actually, in order to implement the 7-segment, then we can define from 0 to 9. Right? It's actually for representing the 1 digit of a decimal number, and we can have 10 cases. But the norm is the 4-bit signal. Okay, so which means that when we use the case statement, we need to define outputs for all 16 cases, right? Because norm is the 4-bit signal. So we don't need to define the other signals, right? Because actually we use the 7-segment for representing 0 to 9, right? 0 to 9. So for this case, we can use the default. So which means that from 10, which means this is A hexadecimal number, 10 to F, we don't need to define the output of this 7-segment, right? So the default. Otherwise, we define the output of 7-segment from 0 to 9. But for other cases, you don't need to define the output of the 7-segment. So in this case, you can use the default, okay, which means otherwise, then output comes from 0 0 0 0. But it's very important, right? If we miss this default, then have to generate latch. That is reserved. Okay, it's very important for using case statement. Okay. And then, actually, for this otherwise case, the default case, we can also use the zeros, but we can also use the non-comparing, right? So when we learned about the kernel map, and then if the truth table includes the don't care output, then we can optimize the Boolean equation more, right? Because we can consider the don't care signal as 0 or 1. Okay, and then so which means it's also same for the this design. So actually, default is otherwise case is not required, but not to generate the correct circuit, then this case statement need to include the default. But we know that actually the 7 segment is used for representing 0 to 9. So which means that input signal, which means none, does not include A to F. So which means that we can define the output of 7 segment using don't care signals. Okay, X. X means the don't care in this case, right? So I explained that X. So we can use X for representing contention, right? Also, we can use X for representing don't care signal. So in this case, X means the don't care. Okay. So we can define the output using don't care. Suppose if we use the don't care signal, then the K2 can consider or this bit can be 0 or 1. So we can difference them. So this can be more optimized. Okay. So when we learn about the don't care signal, right? So if we use the don't care, the kernel map includes the truth table includes the don't care output, then we can optimize the kernel map more. Okay. Okay, this is the wrong implementation. So what is wrong? What is incorrect? Because default is missing. Okay, so and then this is the incorrect design. So incorrect. So it's a bug in hardware design. Okay, so we need to avoid this case. Okay, the bug. And then actually, the software bug that we can debug the software bug because it's just the code, and it's we can modify our code anytime the software code. But this is the hardware, which means that if the hardware is fabricated as a chip, okay, then we cannot modify hardware. So that's why hardware bugs are very, very critical. Okay, if we generate the hardware circuit includes the hardware bug, and then we cannot modify this hardware bug. And then if this hardware bug is very critical, then we need to redesign our hardware module. Then you know, when we learn about the SystemVerilog, the first then we was briefly learn about the hardware design process. So you know, the hardware design process is also very, very complex. It's very expensive. That's the problem. So which means that our design includes the form. Okay, it's very critical. Okay, then our form actually will waste much of money for the form. Okay, so we need to make a hardware chip again. We need to design a hardware chip again. Our system includes the hardware form. So we need to avoid this case. It's very critical. You know, software bug you cannot modify easily. Okay, but hardware bug it's just fixed and it's kind of what was said, right? So we implement our chip using silicon. And silicon is actually sand. Silicon is actually sand or round. So which means that we cannot fix it. So we need to avoid hardware bugs. It's very critical. Okay. You can also define don't care in the input condition. Okay, and then actually it's case C. You should be case C. So if you want to use the don't care signal in the input condition, then you can use the case C. Okay. So in this case, you can observe the question mark here. And then actually for the input of the case statement, question mark means don't care. So what does that mean? So this is the priority circuit. Okay, so which means the first, the MSB is bit 1, and then the output of the priority circuit becomes the 1 0 0 0. Regardless, the result of other bits. Why? So we have to define the priority circuit. Then we can define the condition of this priority circuit like 1 and question marks. Don't care, don't care, don't care. So which means that if the MSB is 1, then output is 1 0 0 0. Regardless of the other bits. And then this is also same. The MSB is 0, and then the next bit is 1, and output is the 0 1 0 0. And then those two bits are don't care. Okay, so in order to use the don't care in the condition of the case statement, then we can use the case 0. Okay, and then you need to remember that don't care in the condition of the case is the question, right? So for the output, we can use the X for the don't care, but for the case statement, if we use the don't care, if we want to use don't care in the input of the case, the condition of the case, then we need to use the question mark. Okay. Okay. Then let's see how to implement the multiplexer using SystemVerilog. Okay, this is the symbol of the multiplexer, right? And then this is the truth table. So firstly, we can implement the multiplexer using SOP form, like the sum of a product form, right? So based on the truth table, we can generate the Boolean equation. Okay, and then we can use the column map like this. Okay, and then which means in the column map, then we can group these two elements for this column map, and then this is the Boolean equation of 2-to-1 multiplexer. And then this Boolean equation can be implemented like this. Okay, so this is the multiplexer, 2-to-1 multiplexer code, SystemVerilog code for this Boolean equation. So the A. Delete this one. So A is the 1-bit signal, A and B are 1-bit input signal, and then this is selection signal, and this is the 1. And then this is the Boolean equation. So it's can straightforwardly implement this Boolean equation using AND operator and NOT operator and OR operator in SystemVerilog, right? So Y is the output. So this is the one example of the 2-to-1 multiplexer. You can also implement the multiplexer using tri-state logic in SystemVerilog. So this is the tri-state module, and the output is defined as tri. So then the output is just connected to the this output Y is just connected to the output of the tri-state gates, and then so it goes input signal. And then this is the selection signal. Okay, so if you see the behavioral model of the tri-state gate, the enable is 1 and A is selected, and then otherwise it's high Z, right? The high impedance. Then we can implement tri-state gate like this. For this tri-state gate 0. So this is the instance name. So it is 0 is this 1. Okay. For this 0, then S is connected to the bubble of this tri-state gate. So it means that it's not, right? So that's why the not selection is connected, right? And then the input A is connected here, and this is the output, right? And then this is the tri-state gate 1. So this is the instance name. So you can find the number 1 here. So this is the instance name. Then this is the same module. So using the same module, we can instantiate the multiple instances. 0 instance 0 and instance 1. Okay. So in this example, the B is connected to the input of this tri-state gate 1, and selection signal is just directly connected. So it's selection. Okay. Then Y is connected. So we can easily also implement the 2-to-1 multiplexer using tri-state gate module. Another example, but usually we can implement multiplexer using 1-9-state mountain. And then we can use ternary operation. Okay. Right, it's very simple, right? Y is the output, the Y is, and then I frequently use this statement because we can implement multiplexer using 1-9 statement. Okay. The selection, and then selection is 1, then B is selected, and then or otherwise A is selected. It's very simple, right? So 2-to-1 multiplexer. Okay. And if you want to use if-else statement, then you can implement 2-to-1 multiplexer like this. But as you can see, you need to use the always statement, always common, for implementing or using if-else statement. Okay. Also, this is very simple. So actually, we use the. Actually, I prefer this one because it's just one-time definition. But you can also use the if-else statement like this, and then you can easily understand the behavior of multiplexer. Right? It's straightforward. Okay. Understand? So usually we use this statement for implementing MUX, the multiplexing. Okay. Then how can we define the 4-to-1 multiplexer in SystemVerilog? If we want to use the assign statement, we can implement multiplexer like this. So what does that mean? So in order to implement the 4-to-1 multiplexer, the selection signal is the 2-bit signal, right? there are 4 inputs, A, B, C, D, and then we need to select select the output out of 4 input signals. Okay, which means that the selection signal need to be 2-bit signal. Okay, then how can we implement the 4-to-1 multiplexer? So if we want to use the assign statement like this, we can implement the 4-to-1 multiplexer like this. What does that mean? Can you understand this statement? So actually, it implements here's the multiplexer. This one. You understand? Using the S0, that is the zero speed of the selection signal, we can select from P0 and P1, and P2 and P3. And then using the S1, then we just select the output of this multiplexer, then work output of this multiplexer. So final out. So we can implement the 4-to-1 multiplexer like this. And then if you see the SystemVerilog code, it's same, right? This is it's a 2-to-1 multiplexer, right? And then it's 2-to-1 multiplexer, select from C or D, right? And then this is another 2-to-1 multiplexer, right? So we can, based on the 0 speed, we can select from the A and B, A or B. And then, which means that this becomes the output of the MUX1. This is the output of MUX0. And then based using the one signal. So it's a selection signal 1, then the final output is determined. Okay, the final output is selected from output of MUX1 or output of MUX0. Okay, so this is the MUX0, MUX1, and then the final MUX. Okay, like this. So we can also, using the one-line statement, we can easily implement the 4-to-1 multiplexer. But more straightforwardly, we can also use this nested as the nested kernel frame. So this is another representation of the 4-to-1 multiplexer. Which means that the selection is 0, 0, and A is selected. Otherwise, and then it goes to this line. Then if the selection is the 0, 1, and B is selected, and 1, C is selected, B is selected. Okay, it's the same, right? Based on the selection signal and Y can be A or B or C or D. But this is the nested if else, right? You understand? So actually, this is the same. Actually, this is the same. Actually, this statement will generate the same multiplexing, but actually, if we use the if else at the kernel data, then it implies priority. So what does that mean? Firstly, we first check the selection is 0, 0 first, and then we check the selection is equal to 0, 1, and then we check if selection is equal to 1, 0. So I said firstly check is what? And then 0, 1, and then 1, 0. So my sentence includes the hierarchy, right? First check something, then check something, then check something. So actually this statement also implements the COSE221 MUX, but it implies hierarchy. So actually, if this statement is straightforwardly synthesized, then this circuit is synthesized like this, like so this is A, then this is 2-to-1 multiplexer, and this is the Y, and then this is the S selection equal 0, 0, and then another multiplexer, this is the B, and this is the selection equal 0, 1, and this is the another multiplexer, then C and D, and then this is the selection equal 1, 0, like this. So this statement is straightforwardly analyzed and synthesized. Then the circuit generator nested multiplexer. But don't worry, but actually, try to optimize the synthesized circuit, which means that the head 2 will generate the optimized circuit at the end. But straightforwardly, it's analyzed and then translated, and this circuit looks like this. So just to remember that when we write those SystemVerilog code, this is hardware. Then when we use the net statement, so it means that it implies hierarchy. And then if we just consider the hierarchy, then it looks like this. This is the generated multiplex. Okay, you understand? So first A is first element is 0, 0, A is selected. Otherwise, B is selected with 0, 1. Okay. So A is the highest hierarchy. Okay. Usually, we can implement the COSE221 multiplexer using case statement, right? So which means that based on the selection is 0, 0, while the A, B, and the C, the both are called B. So not to avoid the bug, just so you can use default by default. Okay. So it's just, I believe you can easily understand the definition of the statement, right? So, and then as I mentioned, not to use the case statement, we need to use array statement, okay? But this statement, you can find some different comment, the special comment actually. So what does that mean? So this is the command, right? This is just the command. And then this full case and parallel. Then this is the special command. And this special command is called program. It's called the program of the SystemVerilog. Actually, this program just delivers the special instruction to part 2, special instruction to synthesis 2. Okay, so it starts with the synthesis, which means that the command starts with the synthesis, which means that this is the a special instruction for synthesis 2. Okay. It is just a command. So which means that this command is not translated during simulation, right? Just a command. Like so when we use the command in our software code, then comment is not translated, right? So for simulation, this comment is not translated, but using this program, then we can give a special instructions to synthesis tool and the simulation tool. So it means that actually the case statement also implies hierarchy. Because the first we check 0, 0, and then check 0, 1, and then check 1, 0. It's the same for the switch statement in C. So the switch statement also includes the hierarchy. Okay, it's just if else. And then it's also same for the case statement. But when you implement the 4-to-1 multiplexer, the 4-to-1 multiplexer does not have any different hierarchies among these 4 inputs, right? Actually, it's parallelly connected to the output. There are no different hierarchies among inputs, right? So actually, this means that even though we use a case statement, and the case statement also implies different priorities for this condition, which means that first check 0, 0, and then check 0, 1, and then check 1, 0 at once. But this is just to give information that actually we do not consider any priority differences between these conditions, which means the parallel case. Then also full case, all conditions are considered. Okay. So if the synthesis tool check this program, then the synthesis tool just use the 4-to-1 MUX block. And then actually the 4-to-1 MUX block does not include any hierarchy. Okay. So this is some special instruction for synthesis tool. It's not translated during simulation. Actually, the simulator ignores commands. It does the command. So this is the implementations of multiplexers. Okay, and then let's see another building block, combinational building block. Okay, so I explained until this one, and then this is the a special form of the multiplexer, which means that we can also implement logic, combinational logic, or Boolean equations using multiplex. So this is the example. So this example shows actually a bar here. So this is the truth table of A and B, and this is the output Y. Then it's the 0, 0, 1, 0, 0. And this is the Boolean equation, right? And then we can implement this Boolean equation using AND gate and then NOT gate, right? But we can also implement this Boolean equation using multiplexer. And then actually we can use multiplexer as a lookup table. So what does that mean? So lookup table means that based on some input values, output values are defined or predefined based on this input value. That is the lookup table. So we can implement this output Y using a lookup table by using multiplexer. So what does that mean? So if you see this inputs of a multiplexer, so this is the 4-to-1 multiplexer, right? And then this is the input when the selection signal is 0, 0, and then 0, 1, 1, 0, 1, 1. And then as you can see, these inputs are connected to 0, and then the selection signal is 0, 1. This input is connected to the VDD, so which means 1. And then this is Y. So what does that mean? If A, B equal, so this multiplexer represents if A, B equal to B 0, 1, okay? 0, 1, then this is connected to 1, so 1. Right. So which means that if A is the 1, 0, 1, this is the Y equal 1, because this is 1. Otherwise, then the input servo these ports are connected to 0, which is ground. So Y is connected to the 0. So A is 0, 0, 0, 0, 1, 0, 0, 1, 1, 0. So we can use multiplexer as a lookup table, right? And then which means that the output is just defined. So this is the output Y, and then using the selection signal, output is just selected. And then using the property, we can implement Boolean equation and then multiplexer. So actually it's same to the, here's this one, right? It's also example of the lookup table. So based on the input selection signal at 0 to 9 and otherwise, then outputs are just defined, right? So so actually we can implement the this statement for generating multiplexer, 16 to 1 multiplexer, and then the outputs are just defined. So we can use the multiplexer for implementing any combinational logic, because we can use multiplexer as a lookup table. Okay. So this is another example. So, and then I think we can easily understand. So this multiplexer implement the AND gate, right? So just the 1, 1 is connected to high voltage, the VDD. So this implements the Y equal A and B. This is the OR gate. So we can implement any logic gate using multiplexer and skill. So this is the OR gate. So 0, 1, 1, 0, 1, 1 are connected to high voltage. So 1. Then 0, 0 is connected to 1. This is the exclusive OR. Right. So which means that by changing the inputs of the multiplexer, we can implement any logic gate. Okay, which means that we can use multiplexer as a lookup table. Actually, so in FPGA, FPGA has many multiplexers, and then we can actually program some gates in the FPGA like this. Okay, it is because if we use the multiplexer, then we can implement any logic gates. Okay. Also, we can implement the logic gate like this. So what does that mean? So actually, in the previous example, the previous example has the 2 inputs, which means that there are 4 different cases. So in order to implement the logic gate for the 2 input signal, then we need to use the 4-to-1 multiplexer. Right? There are 2 inputs, and then which means that there are 4 different cases. And then in order to implement the 4 different cases, then we need to use the 4-to-1 multiplexer. But in this example, this is the Y equal AB. Actually, we can simplify these 2 tables like this. So what does that mean? Actually, it's very simple. So this is the AND gate, so which means that 1, 1 is equal 1. And then actually we already know that if the A equal 1, right, the Y equal B for the AND gate. Right. So if Y equal AB, and then if the A equal 1, then Y equal B. So we can rewrite the truth table like this. If A is 0, Y is 0. So this is AND gate. And then if Y is 1, A is 1, Y is B. Obviously, right? Then we can implement this gate like this. A is 0, then Y is 0, just 0. So which means that 0 is connected to Y. And then if A is 1, and Y is equal to B. So which means that B is connected to Y. Right. So which means that we can simplify. This circuit. So instead of using this 4-to-1 multiplexer, we can implement this circuit or this combinational logic using 2-to-1 multiplexer. Okay. Okay. So I think I will stop here. Okay. So in the next class, we will learn about the decoder and then also the timing. And then our midterm includes what we learn in the next class. Okay. So in the next class, so actually I mentioned that the midterm will cover chapter 1 and chapter 2 of the textbook, and the system Verilog will learn. Okay. So which means that the midterm will cover until we learn the next class. Okay. Any question? Okay. Thank you for your attention and see you in the next class. Come down.